Thank you, Dr. Selahattin. And dear lecturers and participants, my name is Agah Ertay, and it's my great pleasure to attend this wonderful event. And I received, let me introduce myself. I received my Bachelor of Science in Electronics and Communications Engineering in Yıldız Technical University. And I received my Master of Science and PhD in Electronics and Communications Engineering at Istanbul Technical University. Now I have been working as an assistant professor at Erzincan Binali Yıldırım University since 2019. So here I'm going to present traveling wave interaction of TWT, I think. Here is the outline of my presentation. So I will explain introduction. Introduction will be given about traveling wave tubes, and it will be given a general operation principle of a traveling wave tube. After that, the main part of this presentation is traveling wave interaction of TWT. It includes circuit equation, electronic equation, and if you combine this in this section, we have overall equation or determinantal equation, or Peirce four-way equation. If we assume some mathematical explanation, we can have Peirce three-way equation. So we can discuss this. And if we assume some differential incremental propagation constants, and we can obtain a polynomial equation, quadratic polynomial equation. Then we can solve it, and then we can discuss by using these equations. We can discuss synchronized and non-synchronized operation of this equation. So we can discuss how these equations, how these roots of equations can behave in the TWT. So if we include effect of circuit loss and space charge, so how can we see it in the equations? So we can discuss. And the last of two sections are results and gain calculations of TWT using Peirce parameters, which means space charge parameters Q, C, and D circuit parameter, circuit loss parameter, and B synchronization parameter between electron beam and velocity of electron beam velocity and phase velocity of electromagnetic wave. And lastly, we discuss high level interaction, and we have conclusion. So traveling wave tubes are used as a final stage amplifiers in many applications, such as communication satellites and electronic wire phase systems. We can say here typical TWTs consists mainly of 5 sections, namely this electron gun and slow wave structure and input-output couplers, focusing structure, and collector. So what is the purpose of these structures? What is the purpose of these structures? Electron gun block generates and forms an electron beam, which acts as input of slow wave structures for beam wave interaction. And the slow wave structure is a periodic structure block of TWT for propagation of electromagnetic wave during the interaction phenomena. And we have focusing structure, which means that it provides confining the electron beam. So for the interaction process for the interaction process in the SWS slow wave structure, this interaction results in an amplification process, since the energy of electrons is transferred to electromagnetic wave. A system of input and output couplers is connected to input and output terminals of the SWS in order to derive the RF signal at the output coupler and input coupler. At the input coupler, to obtain at the input coupler and output coupler, at the input coupler to derive the RF signal, at the output coupler to obtain required output power of the TWT. Finally, we have collector block. Collector block has an absorption role of the spent electron beam, which has residual energy of electron, electron energy, and contributes to the power recovery from spent electron beam in order to improve the efficiency of the TWT. We can explain this. How we can say how the signal amplify in TWT. We can say step by step. You can think this TWT from electron gun to collector, and we can think these numbers. So number one, electron beam directed through electron beam is created in the electron gun, and then electron beam directed through center of helix in number one. Then number two, continuous wave signal coupled into the helix, coupled into slow wave structures. For this one, we can think helix slow wave structure. The magnitude of force on the electron beam, magnitude of force exerted to the electron beam by the continuous wave signal. So the beam wave interaction can start here. In number two, electron bunching caused by electric field of the continuous wave signal. So we can say electron bunching formation of accelerating and decelerating field regions. So electron bunching starts in number three. After that, we can say amplification increases as the greater velocity of the electron beam pulls the electron bunches more nearly in phase with electric field of the continuous wave signal. And in number 6, we can see a continuous wave signal is decreasing because of the attenuator. We use here attenuator to prevent undesired waves such as waves reflected from mismatched loads and from returning to the tube input and causing oscillation. But when we use attenuator here, electron bunches travel through attenuator unaffected. This is important. This is most important thing. After that, we can think number 7. So electron bunches travels unaffected in the attenuator, through the attenuator. And then number 8, we can see here creation of a new continuous wave signal. So it can start here, and the amplification starts here again. We can see here, number 7, after number 7, number 8, the amplification process starts due to beam wave interaction, we can say. So in number 9, the field of newly induced continuous wave signal interacts with the bunch electrons. So you can see the black dots here. I don't see, but you can see black dots here. These are electron bunch points, charge accumulation, electron bunch points. So field of newly induced continuous wave signal interacts with the bunch electrons to begin the amplification process over again. So after this beam wave interaction, velocity of electron is decreasing, and amplification of electromagnetic wave is increasing. So we must receive output signal before saturation. So we can see number 12. We receive the output signal. So this is a graphical explanation, the graphical representation of a general operation principle of TWT, we can say. Yes. So if we explain traveling wave interaction, Peirce gives a mathematical model and approximate quantitative aspects of mechanism of TWT. So we discuss Peirce theory here, but improved theories based upon a more complete electromagnetic analysis of Maxwell equations into the helix have also been developed by Chu and Jackson. Reference number 6. You can check it. This is more complex than this Peirce theory, but Peirce theory is a simplified one, we can say. So Peirce gives a mathematical model and approximate quantitative aspects. And Peirce uses incremental propagation constants to understand propagation constants of traveling wave tube. It's based on combining and solving circuit and electronic equations simultaneously. To obtain wave-like solutions, actually, we need some assumptions to simply understand the solution of this equation. So we assume that here time and distance dependency is e to the j omega t plus beta z. We assume this dependency to obtain wave-like solutions. And where beta is the unknown propagation constant of the tube. We want to find this unknown propagation constant. Assumption 2, we assume small signal conditions, which means that AC component of the electron beam velocity can be neglected with respect to average velocity of electron. So V is relatively small. V is ignored, neglected to U0. U0 is equal to average velocity of electron. Assumption 3, we can say it's assumed that the velocity of electron beam is relatively slow than the velocity of light. And assumption 4, no transverse motion of electron beam is occurred. This is important because we assume that uniform electron beam pass through the helix. We assume here by solving equations. And another assumption is very small electron beam diameter or hollow cylindrical shaped electron beam is assumed. So we can start to analyze this system. And we can say here how to derive circuit equation. And we can say in the Pierce theory, RF circuit of TWT, which means slow wave circuit. We can model it transmission line as shown in this figure. And if we apply Kirchhoff current law at point A, before that, we assume that here a uniform electron beam is a uniform electron beam passes closely to this circuit. So we can say here I axial or axial component of this IZ can affect this circuit at point A, and we can say capital I equals to minus DIZ divided by DZ. We can write it. After that, we can apply Kirchhoff circuit law, Kirchhoff current law, sorry. As an incremental length for the delta Z, we can write equation 1 here at point A. We can write it, this equation 1. And we can write IC, which means current of capacitance. So we can write it like this, minus V divided by reactance of capacitance.
Is this the current flow for the electron or for the RF?
What?
Is this for the electron beam or for the RF? These equations you are writing.
These equations we are writing is RF.
Kirchhoff.
Yeah, Kirchhoff.
RF or for the electron beam?
RF.
RF. Okay.
RF. Yeah. This IZ is affected here. IZ affects the slow wave circuit, and after this affection, after this effect, then we can write Kirchhoff current law. So we use this for RF. So if we substitute IC into the equation 1, then we can obtain equation 3. here. And if we divided all sides of equation by delta z, and we limit delta z goes to 0, then we can write equation 4. So we can obtain here partial differential equations. Here, equation 4. And if we apply voltage, Kirchhoff's voltage law, or voltage around A, B, C, D, we can apply this, and we can obtain equation 5 here. We can obtain it, equation 5. If we arrange this equation, then we can obtain equation 6. And if we use phasor notation here, then we can obtain equation 7. So if we think equation 4, here, sorry, if we think equation 4, and if we use phasor notation, then we can obtain equation 7. And if we use equation 6, and we use the phasor notation of this, and we can obtain equation 8. So if we combine these equations, equation 7 and equation 8, then we can obtain equation 9. And we know that Ez equals to minus dV divided by dz. So we can write Ez in phasor notation J beta V. So we can obtain Ez in terms of Iz. So this is this equation 10. So this we use this equation. If we eliminate LL and CL, which means that inductance per unit length and capacitance per unit length. If we eliminate this, we use these formulas. We can use these formulas because this is a transmission line. So we can write transmission lines equations. If we assume R equals 0, which means R equals 0 and G equals 0, which means we have no loss. And we can write phase velocity of this transmission line like this, equation number 11. And we can write characteristic impedance of this transmission line, equation 12. And we can write propagation constant of this transmission line like this, and we can write this notation, this equation 14. So if we use this equation in the equation 10, then we can obtain Pierce circuit equation. We can see here Ez can be written in terms of Iz, and we can see here we have Z0, and we have beta C, which means that propagation constant of circuit, and beta is that we want to know this equation. So another point is electronic equation we want to know. The electronic equation is the problem of finding the current within the beam in terms of the field acting on the beam. We know that electron beam consists of two velocities. One of them is AC component of electron velocity. One of them is average velocity of electron. So we can write these velocities with time variation. It's equal to charge to mass ratio the times potential variation of with position. We can write it. After that, we can write AC component of electron velocity. We can write it as partial derivatives of this. So we can write dV divided by T plus dV divided by dZ times dZ divided by dt, and the right hand side of this equation 17. And if we use after this
Hello.
hi.
Yes, sir, I have a question. I want to perceive that how
Yes.
as hello.
Yeah.
Yes. Yes. In slow wave structure, I mean helical structure, where electron are passing through the helical structure.
Yeah.
So the electron beam are not touching the slow wave structure. Is it right?
Electron beam.
Electron beam is going through the slow wave structure. I mean helix.
Yes.
Yes,
Yes.
that means it not physically touch the slow wave structure.
Yes, that's right.
Okay. Now my question is that I want to perceive. Actually, I want to perceive, not by equation. I want to perceive that how a current are transferred to the slow wave structure from electron beam.
Okay. It can be explained. Affecting of electric field and current between beam and electromagnetic wave. Actually, I can say.
Okay. Actually, yes. Hello.
Due to this
Yes.
reason, we can say electron bunching process is started after this beam wave interaction.
Okay. If it's a traveling wave amplifier, what you brief above, but traveling wave oscillator, there have no input RF signal. So if it act as a oscillator, then how this bunching are started? If a small RF signal is induced in the solar structure, then bunching can be started slowly, first small scale, then after sometimes it will be amplified. But in traveling wave oscillator, how these bunching are started? This is the my I can't perceive that, so I made this question. And when electron are not penetrating the solar structure, then bunching are not started right time. Is it right? At the time when
okay. As far as I know, I don't know actually backward wave oscillator mechanism, but as far as I know, if you change the input and output of RF input and output of the system, I think the process is different from TWT.
Okay. Okay, but when bunching are started, then I think then time varying magnetic field are generated and which are touching the solar structure and then energy transfer. Is it right? My perception is it right? I mean electrons when bunching they are accelerating. Is it
Yes.
right?
Yes.
Okay, then as it accelerating, then time varying magnetic field are induced.
Yes. Yes, of course.
Then these magnetic field are coincide with solar structure.
Yeah.
Then energy transfer. Is the process? What I am explain?
Yeah. You are right. I think because.
Okay.
Yeah, you are right because electron beam pass through the helix, and this induced a current. This induced a current in the helix.
Yes. 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 Okay. Some magnetic time varying magnetic field interaction are happen in the helix. I
Yeah.
hope so.
Uh-huh.
Okay. Another question is that if electron beam is not close to the helix, then is it affect this its output power?
I can. Can you repeat, please? Can you repeat?
Okay. If electron beam is not close to the solar structure,
Yes.
then output power will vary.
Output power.
Okay.
Output power.
Output power will increase or decrease.
Output power increase or decrease?
Yes. Is it increase or decrease?
I think it's not increase actually because
Yes.
there is no beam wave interaction.
Yes. But okay. That means it's beam wave interaction. That means maybe their magnetic field interaction is not too too dense.
Yeah.
As it's
You can say that this is cold process. Because
okay.
there is no beam. We
Yes.
just analyze this helix wave structure.
Yes.
Uh-huh.
Okay. Okay. That's my question. Okay.
Thank you.
So perception. Okay. Thank you, sir. Thank you.
Thank you. Any question? Okay. Then we have here equation 17. We have here, and if you look at this, sorry. If we neglect some AC quantities in 17 due to small signal assumptions, small signal conditions assumptions, then we can write equation 18. And we can write this equation 18. What is the small signal assumption? We neglect AC component of velocity of electron. So we have average velocity of electron. So we have here equation 18. So we can write this in phasor notation. So we can obtain equation 90 here. And if you look at equation 20, we can write propagation constant of electron omega divided by u0. And if we substitute this equation into equation 19, then we can obtain equation 21. We can write this AC component of electron velocity in terms of EZ, beta E u0. We need this equation. If we think continuity equation, we can write this equation 21, diz divided by dz equals to minus d rho divided by dt. If we use Phasor notation of this, then we can write equation 23 here, and we can write here the total beam current. Total beam current here is equal to total beam velocity times total charge density, which both of them contain AC and DC component as shown in equation 24. If we write rho 0 in equation 25, and we can write u0 equation 27, and we obtain AC component of electron velocity in equation 21. And if we neglect some of the equations with the small signal assumption and applying the equation of conservation of charge to obtain AC linear charge density in terms of beta and Iz, then we can write equation 28. We use this 25, equation 25, we use this, and we use 27, equation 27, and we use 21 in equation 26. And we use assumption of the small signal condition. So we can obtain Pierce electronic equation here. Iz can be written as in terms of Ez here. So we have two equations here, and Pierce circuit equation and Pierce electronic equation. If we combine them here, we can obtain equation 29 here. This is actually a four-wave equation, Pierce four-wave equation. Pierce here defines a quantity called gain parameter here, C, small signal gain parameter. C can be defined as Z0 divided by 4 Y0 V0 divided by I0. V0 divided by I0 is defined as beam impedance. Z0 is defined as circuit impedance. In some books, in Pierce, for example, in Pierce book, this can be defined as interaction impedance, written as K. K equals to E0 square divided by 2 beta square P. E0 axial component of electric field, and beta propagation constant of the slow wave structure, and P is power flow. So if we substitute equation 30, which means small signal gain parameter, into the equation 29, so we can obtain 31, equation 31 here, equation 31. So this is Pierce four-wave equation. It can also be solved numerically But if we obtain some assumption, we can use Peirce three-wave equation here. So here let's talk about synchronized and non-synchronized operation here. We want to solve this equation 31. We want to solve it, but we can say here we can have synchronized case and non-synchronized case. Synchronized case means that beta E equals to beta C. Beta E, propagation constant of electron. Beta C, propagation constant of circuit, flow wave circuit. So this is synchronized case. If we assume that beta differs from beta E by only a small amount of zeta, so we can write beta here, beta plus zeta. Or we can write this beta C plus zeta. If we substitute beta in equation 32 to equation 31, if we substitute it, then we can obtain 33, equation 33. So we have some assumptions here. We have some neglect. We have here, because beta is expected to be close beta E, so zeta smaller than beta E. As a result, we can neglect some of terms here. Beta E times zeta and zeta square can be neglected in comparison to beta E square in the numerator here, and zeta square can be neglected in comparison to beta E zeta in the denominator. With these approximations, we can obtain equation 34. So this equation can be written as equation 35. So this is complex root finding problem. So we can find it actually. So if we solve this equation 35, so we can find it 3 complex roots here. How to say it? I think she or something like that. She1, she2, she3. We have 3 complex roots here. If we substitute these 3 roots into these equations 32, now we can have here beta 1, beta 2, and beta 3. But how can we classify these results? How can we classify it? We can write beta 1 here, beta E plus she1, beta E C. We can write beta 2 here, beta E plus she2, beta E C. And we can write beta 3 here plus beta 3 here, beta E plus she3, beta E C. We can search these results actually, but we need here phase velocity of slow wave circuit, as you can see the right side of this slide, and we need to analyze average velocity of electron here. If we think about that, then we can say here, in beta 1 and beta 2, the quantity here, beta E C divided by 2 in beta 1 and in beta 2. This indicates that the wave travels slower than the electron beam. we have another solution. If we additionally we have the backward wave solution, when the backward wave solution is also performed, then we can write phase constant or propagation constant of the fourth root. So we can write minus beta E plus beta E C to 3 divided by 4. So we can write, if we think about this equation, we can say here the wave travels in the direction of opposite side due to the minus sign of this. So the wave travels in the direction opposite side to that of the electron beam. In beta 1 and beta 2, the imaginary part, we have imaginary part here. Imaginary part of the propagation constant indicates that the wave is either a growing wave or a decaying wave. We can say here, this is a +1 in beta 1. This is a growing wave. This is a -1. Beta 2 is decreasing wave. And we can say here, phase velocity of electrons are slower than speed of electrons. We can say it. So that's all. So we can classify these roots, I think. So we can say this is beta 1 slow forward wave and beta 2 slow forward but decreasing wave, and beta 3 fast forward and unattenuated wave. And we can say beta 4 fast backward wave. Here we can classify these roots. Another case, actually, non-synchronized operation. We can pierce here. It's actually pierce. We can introduce pierce parameters B. It's helpful to produce pierce velocity parameters. This is velocity parameter or synchronization parameter between beam and wave velocity. This parameter is used to relate the DC electron velocity U0 to the phase velocity of the circuit in the absence of electrons. So we can analyze, for example, for B greater than 0, we can say B greater than 0. If we check equation 41, we can say for B is greater than 0, the electrons go faster than the undisturbed wave. Undisturbed wave means the phase velocity of electron. And for B is less than 0, then the electrons go slower than the undisturbed wave. For B equals to 0, then the synchronous case occurs here. So another point, synchronous case means that beta E equals to beta C. Non-synchronous case can be explained, beta C equals beta E times 1 plus C times B. If we talk about effect of loss and space charge, so we can define, we know here, we can write beta C equals to beta E times 1 plus C times B. If we taking into account the effect of circuit loss, effect of loss due to RF circuits or RF circuits and backward wave, we can take all of them. We can add here loss parameter. We can add this loss here. minus J beta E C D. We can add this parameter. So this is also this can be written as this is J alpha actually. So we can write D here, alpha divided by beta E C in equation 43. If we look at the right side of this slide, we can say if we have beta E times Z, if we equate this to 2 pi n, we can write beta E here. We can write beta E 2 pi divided by lambda, and we can write Z here in terms of lambda n. So we can define loss here. So 20 logarithm e to the minus 2 pi n c. So we can write attenuation in dB form here. 54.5 CD dB per wavelength. So we can write attenuation here in terms of in Nepper 0.0184 attenuation divided by small signal gain parameter C here. This equation 44. If we think about space charge, now we use these two equations, Pierce electronic equation and Pierce circuit equation. If we think about circuit equation, Pierce circuit equation here, then we can write EZ here. If you look at this EZC, which means that electric field due to this circuit, just circuit, no space charge. If we taking into account the effects of space charge, then we add electric fields of the space charge here. So how can we obtain this space charge of electric field? So we use here Poisson's equation. We can define here equation 45. If you look at this, we can write this equation 45 in phasor form. Then we can obtain 46 here. And we can write equation 47 here, like this. And we can write this in phasor form. Then we can obtain 48 here. So if we use 48 into 46, then we can obtain 49 here. We can obtain this. And if we substitute this equation 49 into equation 15 here, Pierce circuit equation, then we can write equation 50 here. We can write it. So we take into account the effects of space charge here. Next, after this process, we obtain equation 50. So if we combine equation 50 and equation 28, then we can obtain another equation here. If we combine these equations, we can write equation 52 here. We can write it. Yes, this equation. So we have some mathematical manipulations here actually. We use these manipulations and we obtain here equation 53 here. So this is our equation. We need to solve this equation. This is a four-wave equation. This is four-wave equation. So we can see the difference between equation 53 and equation 31. The difference is here beta q square divided by beta e. This is a measure of the significance of the space charge force. We can say here. And so this is last equation 53 here. So if you let's assume beta equals this equation, beta equals to beta e times 1 plus c times b, and we can write beta c like this, and we have here a loss. Beta c equals to beta e times 1 plus c times b and minus j beta e c d. And if we ignore j c delta jb and jd compared to the unity, and we can use here this notation 54. This is Pierce notation. So delta is equal to x plus jy here. And if you use these notations, then we can obtain this simple elegant form of equation here, 56. So we can write 4qc here, beta p divided by c beta e square. Pierce calls q here the space charge parameter. Using his capacitance approach, its value can be defined as this equation 58, and C1 here, this is capacitance per unit length, can be defined as 59 here. The effect of space charge could be represented here by capacitance between beam and the circuit here. So we can say that the meanings of space charge parameter Q and QC are not straightforward. However, by rewriting for QC as follows, the physical significance can be inferred by using equation 58. Here we can say the ratio of plasma frequency here to RF frequency, plasma frequency omega p, RF frequency omega, is a measure of space charge debunching forces here. Pierce gain parameter C is a measure of intensity of the interaction between slow wave circuit and the electron beam. As a result, QC is a measure of relative strength of debunching forces to bunching forces. Thus, QC has been adopted to describe the seriousness of the space charge effects in traveling wave tubes. In here, for finite beams, the plasma frequency WQ is less than its for the infinite beam. WP and WQ should be used in the expression of for QC here. this equation 60. So we have here dimensionless parameters here. Equation 56, and we can define C, we can define B, we can define D, and we can write Q here, and we can write QC. So this is, and we can write delta here. We can write delta. So this is Pierce three-wave equation here in dimensionless form in terms of his incremental propagation constant. This is incremental form. So we can solve this equation numerically. We have here three solutions of delta, depends only on the four dimensional parameters, C, B, Q, and D, representing respectively the strength of mode coupling in the beam circuit interaction, also known as Pierce gain parameter or coupling constant. B is the degree of synchronism between the beam motion and cold circuit wave, and Q, space charge effect, shows space charge effect, and D represents the cold tube circuit loss here. So if we solve this equation 56, if we solve this equation, then we can say something about interesting here. So if we comment this, we think these equations up there, we obtain these equations, these results here. We can plot this x and y. We can plot this x and y to the velocity parameter here. So x1, we can think x1 and y1 here. If we check this equation, right side of this 61 and 62. If we think about these equations, for example, 61, we can see here x can contribute amplitude of this incremental amplitude, can contribute amplitude of beta, and y can contribute velocity of electron beam, or yes, electron beam, or we can adjust this. We can say something about phase velocity, between phase velocity and electron velocity here. So if you think about the velocity parameter B here, so we can say that here x1 is a growing wave when beta increases. After this equation, this limit, for this beta equals to this number, then increasing wave is I think 0 or something like that. Before that, this x1 is an increasing wave, you can see here, and after that it can be changed here. So another graphics we have, by the way, we can we assume here no space charge and no loss. We assume this condition here. If we assume that, then we can obtain this graphics. And if we show the right side of the plot figure, we can say here delta 1 is increasing wave component, delta 2 decreasing wave component, and delta 3 is here unattenuated wave. So we can say fourth quadrant, delta 1 is in the fourth quadrant, and delta 2 is third quadrant, and this delta 3 is a y-axis of this figure. So we can plot different number of circuit laws. We can plot it. In here, we assume no space charge. Then we can plot other types of graphics here. So if we increase the circuit loss, then we see here delta 1 goes to smaller. You can see delta 1 goes to smaller here. So the loss is the loss affects the increasing wave condition. And if we just change space charge here with no loss, then we can obtain this graphics, and we can say some assumption here. If we select this case with no loss and QC equals to 0.25, then we can obtain these graphics here. So we can see some of interval here, velocity parameter. We have increasing wave x1, and we can say here y component of 2 and y component of 1 is the same. We can see here, and how can we say yes? So if we increase the space charge effect, then we can say x1 becomes decreasing here and shifting. If we change both of them, then we can see effect of this incremental propagation constants here. So if we explain results and gain calculations of these solutions, so we can write this equation 64 here. If we write just for beta 1 here, remember that we use time and distance dependency e to the j omega t plus beta z. So if we write this for beta 1, then we can obtain here equation 63, and if we use equation 64 here, if we substitute this equation 64 into the equation 63, then we can obtain here is a power gain. So power is proportional to the square of the electric field. So the power gain can be obtained this 47.3 Cn here. Equation 65 gives the gain for the lossless case. So this does not include losses that occur when a signal launched on an electron beam. Since 3 forward waves launched on the beam, a signal applied to the input of a TWT must divide in some way among these 3 forward waves, and so only portion of the input signal is used to launch growing wave. Yes, if we obtain a gain of TWT, then we use a boundary condition here. So to determine the relative amplitude of the launched waves, we use boundary condition here. So 3 waves must add to give the correct RF field and velocity and current. So we can write here equation 66 and 67 and 68 at the input of the traveling wave tube. And from the phase force equation, we can write equation 69, 70, 71 here. And if we substitute equation 72, 73, 74 into the equation 69, 70, 71 here, then we can obtain equation 75, 76, 77 here. If we apply a boundary condition at the end of the traveling wave tube, then we can obtain, finally we can obtain these equations. Yes. Finally, we can obtain this equation. Equation 89. This is power gain. This asymptotic version of this power gain. So this is valid for synchronized case with no loss, no space charge, and no initial current on the beam. So we can write this equation A and B in equation 90 and equation 91. So we can say here at the initial case of this traveling wave tube, we have initial loss here. We have initial loss. If we calculate exact power gain, then we can write this equation 93 here. 93. So if we compare it, we can see we have here initial loss when Z equals to 0 or Cn equals to 0. We have initial loss here. We just think about asymptotic version. If we think exact version of power gain, then we can say gain starts from 0 here. So this is an example. A TWT operates under the following parameters: beam voltage V0 equals to 3 kilovolt, beam current I0 equals to 30 ampere, characteristic impedance of helix Z0 equals to 10 ohm, circuit length M equals to 50, frequency F equals to 10 gigahertz. Determine gain parameter and output power gain in decibels. So we use equation this, you can see, and we obtain this solution here. And if we use asymptotic calculation of power gain, so we can write minus 9.54 plus 47.3 Cn. And if we write Cn here, then we can obtain here 59.52 dB for asymptotic power gain here. If you think about, if you taking into account all parameters here, which means we use all kinds of things: synchronization parameter, space charge parameter, and circuit loss. And we use all of them: V1, V2, V0, all of them. And we apply here boundary condition and boundary condition, so we can extract V out and V in. So if we divide V out to V in, and we can write gain total in dB form like this. If you think about just increasing wave, then we can write incremental gain here. If you think about just increasing wave, so we can write gain increment here. We can write it, and if we calculate this for certain Cn, then we can write this. We can obtain these results here. So this can be plotted for different space charge parameters and different synchronization parameters here. So if you look at this, when Cn equals to 0, we have here initial loss here. After Cn increases, then we can say gain increases here. Gain increases here. If we take into account all waves, beta 1, beta 2, beta 3, then we can obtain gain here for different values of space charge parameter, circuit loss, and velocity parameter here. So we can obtain these graphics here. You can see. So if you look at this, we can say if one synchronization parameter increases, then slope of increment gain is decreasing here. And yes, and when space charge parameters is increasing here, then slope of this values is decreasing here. Yes. So this is last section. We can say here high level interaction. Before this, we can explain electron bunching here. As the beam enters the RF circuit of the TWT, the actual component of the electric field from the circuit accelerates some electrons and decelerates others to start the formation of bunch, as indicates in this figure. So the resulting RF current in the beam induces a current and voltage on the circuit that lags behind the initial voltage by 19 degrees. Thus, induced wave travels more slowly than the initial wave. As the bunches and the induced wave grow, decelerating field regions develop where the bunches are located, as shown in this figure. The energy extracted from decelerated electrons is transferred to the circuit field, thereby producing amplification of that field. As long as small signal conditions exist, Pierce theory applies and the various amplified waves on the beam and circuit grow exponentially with distance, we can say. So in this figure, we can describe saturation here. This is a large-scale model of TWT was constructed here. Using an electron deflection system, the electron velocities and currents in the beam leaving the TWT interaction region were measured as a function of phase position. So x-axis is a phase position, and in this figure A, dry level was well below saturation, and the current and velocity patterns were representative of small signal conditions. The first evidence of nonlinear behavior occurred at 17 dB below saturation. The next pattern is at 12 dB below saturation here. So at 12 dB level, we can say a spur on the velocity curve here, and further development of electron bunch between plus 60 degree and 180 degree. The next two patterns, D and E, next two patterns show continued development of the spar here. The continued movement of electrons from high velocity regions and continued consolidation of the main batch just ahead of the spur here. And the other figure here, if electron velocity pass through the helix, they have electron density, they have electron velocity, and after some distance, we can see here electron velocity get multivalent region here, multivalent region. So this shows, actually, this can be inferred. It's going to saturation. We can say here. And we can say from this figure, circuit voltage after beam wave interaction, the circuit voltage can circuit voltage becomes increasing here. So in this, after evaluating this figure, we need some modification in slow wave structure. So some studies are taken here. Dynamic velocity taper at the end of the slow wave structure. So the pitch of helix is dynamically tapered at the end of the slow wave structure. By doing this, improvement of the efficiency of the TWT can be obtained here. So in this presentation, controlling of maximum gain in the desired frequency region is important, and the searching of maximum gain variations of TWT device with slow wave structures is considered here with using Pierce parameters, and we demonstrate here gain variations of TWT with different Pierce parameters. And Pierce parameters are crucial parameters to control the gain of the TWT for designers. High level interaction is another important point for improving of efficiency of TWT, we can say. So this is many references Some important references here: Pierce, Gilmore, Basu. Yes. Do you have any questions? Zoom? Or
Okay. Is there any question from Zoom? Okay, thank you very much, sir.